now that we've got a bunch of drill holes in there. Well, we don't actually have all the information. Most of the drill holes that have been put in the last 10 or 15 years have been proprietary. We know a little bit about it. But I tried to describe as much as I could with these colored things. I told you the bottom temperature of the well and the depth. And so you see some of these are quite deep. They can go almost 2.5 kilometers. The well temperatures are very high, 300, 350 degrees centigrade. The white ones with the black dots are ones that were hot but just did not produce. No permeability, not enough fracture porosity. The red ones are the producers. The lower red one is HGPA, and the higher red one was one of the first PGV wells, KS1, I think. And then the blue ones, the 3 blue ones, were the scientific observation holes. Those were also mostly publicly funded scientific holes, narrow bore, but they were cored, and we got a lot of information out of those too. The contour map under it is actually based on the temperatures of all these wells at 400 feet below the surface. And you can see that the high temperature area is actually very narrow, and it's centered around the 1955 eruption, the 1955 fissure in the Puna area. And this is a cross-section through that area. The red lines are temperature contours, and in the back it's sort of faded, but you can see some mineralized zones. These are different grades of minerals going from relatively low temperatures to high temperatures. The lowest one, the epidote, and this is all secondary minerals that are sort of sealing up the cracks and things. But the epidote minerals are not present in a few of the high temperature wells. The red bar is where the 1955 dike would have been, where he is. So some more general things about the resource from the results of a few drill holes. It's in the industry, I guess it's characterized as a 2-phase liquid-dominated system. When you pump it out, I gather, and again, I'm not an industry expert, but as you pump it out, you get steam and water together, 2 phases, but it's liquid-dominated. And the literature talks about the fact that this is what, say the geysers geothermal field or the Italian one, Lordirello, looked like sometime in the past. And so sometime in the future, one would think the Kilauea one will go into a vapor phase 2. I suspect that might not be right in the fact that we are on an active volcano and we'll continue to put heat in there in the form of future eruptions. But these are some cartoons about what's down there. You can see the cap, the mineralized cap that keeps the water separated from the shallow groundwater table. There's a heat source down below in the form of some sort of volcanic structure, either a reservoir or a dike. And there's some sort of circulation. There's also some data about the gas content of the fluids. And so they're fairly low, actually even low compared to Kilauea gases, less than 1% by volume, by weight. So how big is the reservoir? A lot of different estimates for this, but the tabulation up on top, if you just breeze through it, you can see that people are estimating that you can get several hundred megawatts of electricity out of the Lower East Rift Zone. There are several different ways for estimating that. The one that makes the most sense to me is you figure out how big the area is that has hot water in it. You figure out how much hot water there is. You convert that to thermal energy by knowing what temperature it is. And then you work out how much electricity you can get out of that. The really interesting thing, though, is the bottom set of numbers, which is what's the rate of adding heat to Kilauea, since it's an active volcano. It's not just sitting there being exploited for its residual heat. It's actively erupting. In the future, there will be more and more dikes going out that area. Heat will be added. And so there's a difference between thermal heat and electrically recovered heat. The thermal heat is quite high. It's in the gigawatt range. But if you really want to look at just that area that's currently being developed, probably the estimate on average is about 100 megawatts being added. Hazards. As I mentioned in the early 1980s anyway, the USGS came out and pointed out that the area that is most attractive for geothermal development, attractive because it's got all this heat and all this water, the heat has a bite to it. It will actually erupt. These are the highest lava flow hazard areas in the state. There are actually also hazards for tephra and subsidence, just what rift zones do. And so it seems like any development plan should take that into account. If an eruption should disrupt geothermal development, it's not going to disrupt it for a few minutes or a few hours. It's going to be days to weeks probably. Oh. The green contours are the seismic hazards. These are the expected shaking intensities in terms of G, which is the acceleration of gravity. And to make sense of this, you see the lowest contour is a 1. So that tells you that all the areas south of that line, there's a 10% probability in the next 50 years that that area will experience 1 G of acceleration or greater. Now, if that acceleration is in the vertical direction, that would leave you airborne. Most of the larger...
What does that mean, sir? Could you please explain it? You're talking like way up here. Can't you just like drop it a little bit and explain what you just said in civilian terms?
1G is the acceleration in gravity. And so if the Earth shakes with a force of greater than 1G in the vertical direction, and the earthquake would make the Earth go up and down, you would be left airborne. Because the Earth moving is exerting a force greater than gravity that's keeping you on the Earth.
Your car would jump around.
Sorry?
Your car would jump around.
Oh, yeah. So we've been asked a number of questions about various aspects of either developing geothermal or whatever. And like I said, we're not industry experts, but we can answer some of them. Can drilling into a magma chamber start an eruption? And although we don't have a definitive answer for that question, there are a few examples of geothermal drills going into magma bodies, and none of them have started eruptions of any kind. Any lengthy eruptions. The one in Iceland in 1997, I think, erupted for about 15 minutes, small amount of spatter and such. But in all of these cases, the well was put into production. It didn't affect the production at all. It went into the magma probably sealed off around the well, and the well continued to be used.
They weren't drilling in Iceland when that erupted, right? The well had already been drilled in Iceland, and the magma intrusion came in and came
The last one, yes, the 2009. 2009 they drilled into it. The 1977 one, I think that's right. The dike found the drill hole. And then the corollary to that is, can an eruption disable a geothermal power plant? I've already talked about that. The sort of warning we would get for such an eruption would be on the best days to weeks, and the eruption could last for days to weeks, therefore the power disruption could be days to weeks. Now, seismicity, we've also been asked about seismicity and whether the drilling affects seismicity or vice versa. We've known for a while, in fact, that was one of the reasons that HGPA was selected, or the well was sited in this particular area, is it was because it was a persistent source of earthquakes. In the Pu'uhonua area, most of them were quite small, but they were still clustered in this area. This is a time series of the cumulative number of earthquakes that occurred from 1960 to 1980. And of course, there was an eruption in Kauahikaua in 1960, and after 1960, you can see in those little bumps in the curve that there were sort of pulses of seismicity. In 1975, we had the large magnitude 7.7 earthquake, and that changed things forever on the south flank. It really invigorated seismicity on the south flank, so you can see the large jump in the number of earthquakes all over the south flank. And this is a plot kind of bringing us up to the present. One of the concerns, of course, is injection, generating earthquakes. And you can see injection starts in 1992, which is at a time when there wasn't a particular increase in earthquakes. But that sort of fits in with the whole idea that there are earthquakes there to begin with. It's an active volcano. There's seismicity along the rift zones, along the south flank. And it doesn't seem so far that injection affects that significantly. Just to give you an idea of our coverage of the Lower East Rift Zone, our stations are in red. The yellow ones are a seismic network that the PGP, the Ormat people installed, that they have kindly allowed us to get access to. We haven't connected to it yet in a robust way, but we intend to. Now, the idea of fluid injection, certainly you can generate earthquakes because you're cracking rock by injecting fluid into the ground, especially when there are fractures already. And so this is a sort of a probably too much information about exactly what happens, but let's go to this example in Newberry Crater. The Newberry Crater is felt to be a hot resource, but there is no hydrothermal system to speak of. So the idea here is to use an existing well and pump water down it. This will start to open up fractures that are already there. The water will be extracted by a couple of other wells and put into a geothermal generator, I guess. Now this is distinctly different from the process of fracking, or trying to generate natural gas reserves out of shale. In that case, you're actually breaking the rock, whereas in this one, you're using high pressure water to open up cracks. Basically, they're already there. As I mentioned, the whole makeup of this subsurface area in the rift zone is a number of cracks, interflow areas. One of the other questions is whether an earthquake can disrupt the geothermal well or cause uncontrolled emissions. And again, we can't answer that definitively, but we can point out the experiences, the interactions between geothermal wells in Hawaii and large earthquakes, as we've had a few of those. Unfortunately, HGPA was started just after the magnitude 7.7 earthquake, so we don't have that as an experience point. But HGPA continued to produce through the two next largest ones, which are a 6.2 and a 6.7. The PGV production started in '92, and it weathered the 2006 earthquake. Of course, that earthquake was on the west side. But the 1975 earthquake did not affect the operation of the summit well up here. It did not shear it off or anything. Almost no effect. Gas hazards. So there is gas dissolved in that hydrothermal brine. And that's pumped out, used in a binary system by PGV, and then pumped back into the ground. The estimated emissions from a blowout, so a blowout is basically all that gas being flashed into, or exhaled into its gas form. And using the data from the 1991 blowout, it looks like the H2S emission rate is about 1.6 tons per day, if you convert it to the type of unit that we use up here. And just a reminder, SO2 up here is emitted at a rate of about, I don't know, about 700 or 800 tons per day currently. So the H2S was coming out during the blowout times at about 1.6 tons per day. H2S emission rates from Pu'uo'o typically are about 5 tons per day, from Halemaumau about 25 tons per day. The 1991, there was a fairly extensive set of reports about the 1991 blowout, and this was an effort to model the dispersion of the gas. So the concentrations fell off rather rapidly from the source. They were measured at up to 30 parts per million at the source, but the numbers that are in kind of square brackets were the ones that were measured by the air monitoring equipment at the time. They're still up in the hundreds of parts per billion or the single parts per million. This is an average over 2 hours. So there are a number of hazard air concentration limits, I guess, that are advised for healthy interactions between humans and these gases. And they're quite different, actually, between what was in existence in the mid-1970s and what is there now. The Hawaii State ambient air quality is 0.025 parts per million for an hour. And the acute exposure guideline is 0.33 parts per million for 8 hours. So if we look back at the KSA blowout, which is again about 2 tons per day for hydrogen sulfide, the maximum was 30 parts per million at the drill site. We don't know how long that was. In the 2006 cleanout accident, there was just under 1 part per million for an hour. PGP was cited for that. In the 2011 lightning strike, it was reported to be 0.062 parts per million. Now, the typical concentrations at Halemaumau right now, even though H2S is a minor component of what's coming out of Halemaumau, is typically less than 3 parts per million, but that's at the same place where the SO2 concentrations can be up to 300 parts per million, so you don't really notice the H2S. The Rotorua, New Zealand, there's a chronic H2S exposure level there, but it's 0.143 parts per million. So these are again the standards. And the air quality monitoring sites. And then PGV does post some of the data from these sites on their website. And that's it. So now, I think it'd be good if we sort of bring up the house lights and get some questions with my co-authors. Yes?
If I may, I suppose that is there not some way to more effectively model the air impacts and actual quantities of H2S that come out of the well by actually getting the data from the wellhead?
Well, I think that's what was done in that post-blowout study.
Well, that's the thing is that during the blowout, all of their equipment went down.
Right.
They recorded, modeled, gathered nothing. And
But there was some portable equipment, right? I mean, they had some data for these models.
Well, I mean, those are estimates gathered by handheld units.
No, at least the way the report reads. You see these numbers in brackets?
Yeah, I have that report.
Okay.
Goddard.
Aren't they describing those as actual measurements that they're sort of calibrating the model up?
Well, but I mean, again, as Mr. Goddard, Dr. Goddard, who was out here and gave an extensive report on this at the time, told us in a meeting in Kauahikaua that the numbers that he was using, he did not like the way they were gathered. Okay, because the State Department had held some number of hours into the 41-hour event.
Right.
Was out there running around with these portable monitors that were not certifiable.
Right.
The air stations many of the air stations had questionable methodology in terms of the placement of the gas intake units.
But your question was about the model.